now for our second presentation, we have Xiaodong Luo from Sabre Holdings.
Thank you, Alan. It is quite an honor to be here presenting our work. My name is Xiaodong Luo. I work for Sabre. The title of the talk is Airline Crew Augmentation, Decades of Improvements from Sabre. First, let me give you an overview of the crew scheduling process from the airlines, so you have a context of our work. Typically, the airline crew scheduling process is divided into two different phases. On the axis is a timeline. So the first phase of that planning process, of scheduling process, is to do the plan. And at some point, the plan is handed off to the operations to execute on the plan. The crew planning phase is also further divided into pairing generation and roster generation, two different steps. So overall, there are usually three different areas that advanced OR techniques can be applied to this process. This is a very complicated process. The first place where OR can play is during the pairing generation. A pairing optimization is to take in the flight schedule as input and generate anonymous pairings which are optimized with minimum cost. The second place where OR can play is roster optimization, which does the roster generation, which takes input from the previous step and assign it to the crews along with other tasks. So the goal of crew scheduling is to create and assign work to the crew members with minimum cost. And the third place is during day of operations is a recovery optimizer, which constantly optimize to minimize impact of disruptions to airlines to bring the airlines back to their normal plans. So you can execute on the plan smoothly. The focus of the talk is on the pairing optimization. In particular, is on the crew augmentation in the context of cockpit pairing generation. So the motivation of our work is the staggering fact that the cockpit pilots, they're costing a lot of money to the airlines. So to give you an example, for large airlines in North America, their airline total cost is around $40 billion annually. 8% of that is approximately $3 billion. So pairing optimization is the first step of the crew scheduling process, and it is a dominant factor to controlling that cost. So the pilots, they are costly because of the work they perform. That is very important. So they are performing the task of pairings. The outcome of the pairing optimization, here's an example of a pairing. What is a pairing? Pairing is a sequence of flights, some of which are performed, pilots are operating on those flights, which we call them operating flights, some of which are deadheading. The purpose of deadheading flights is to move the pilots from one location to the other, where the pilots are not doing the work. They're resting there. So the pairing is a sequence of flights that bring the pilot from his home base through a sequence of work and positioning of flights and come back to his home base. So this is an example of 5 operating flights, 1 deadhead flights in the end. Some of the flights that they closely connected together, they form a day worth of flying, which we'll call duty. They are denoted over here, and the duties themselves are separated by the rest between them, where the pilots go to the hotels and rest for a day or sometimes multiple days. Here we have an example of a pairing from Dallas-Fort Worth going to San Francisco, layover at San Francisco, and ultimately coming back to the home base, Dallas-Fort Worth. So every component of this pairing, this is a pairing, will cost airline money, which contributes to the overall pairing cost. For the sake of this discussion, I just list 3 dominant costs for the pairing. Every airline actually have different cost structure. So assume, for the sake of discussion, for the example I show you, the cost of pairing is mainly constituted of the following 3 parts. The crew days. Crew days is the number of days the pairing touches. Calendar days the pairing touches. Here we have a pairing which touches 4 calendar days. And the hotels. The number of hotels also is the money that the airline spend for the pilots to stay and rest. And deadheads is the money that airlines spend, is lost sale revenue due to the pilots, they occupy some first-class seats usually when they're deadheading. So for the sake of comparison in the cost of the solutions, we'll use these three components to compare the cost. Also, we'll simplify the pairings to look like this. So we'll remove the layovers and all those. So what is crew augmentation? Here you have two pictures. To put it simply, the crew augmentation is airline. It has been used in existence for more than 30 years. It is airline to put extra pilots on the flight, simply for safety reasons. For long flights, for longer duty days, longer duties, by putting more pilots in the cockpit, then it reduces the possibility of human error, right? And for large aircrafts, that is a picture on the right, they usually are the bunk bed where the pilots can take turns to rest. So if you assign more pilots, they can take turns to rest, increase the safety. There are three important aspects of crew augmentation throughout this talk. The first and foremost is dynamic nature of the crew requirements. How much extra pilots are needed actually is not only dependent on the flight characteristics alone. It's not just how long the flight are, it's also how long the duties are that is covered in this flight. Also, it is the duration of the rest that before and after the duty. So the whole formation of the pairing matters. And we'll look at all these three aspects in more detail. The first one is on the dynamic requirement part. Let's quantify that crew augmentation requirements. The airlines usually divide their pilots into two separate groups. One is a captain. The first officer is the second rank. The captain is the top rank. And the augmentation requirements, the crew that is required from for a flight, usually coming in as a group of pilots that is needed. So we're seeing here three different crew teams, or we call them crew types. The basic crew type usually consists of one captain, one first officer, is a crew type all flights need. And for some more longer flights, longer duties, augmented crew are needed, where you add one captain to the basic crew. And the third type, crew type, is double crew, where you add yet another first officer to the augmented crew. The second aspect of crew augmentation is crew splitting or crew teaming concept. They are opposite to each other. What do we call crew splitting? Crew splitting is when the team of pilots, they are not staying together for the entire duration of the pairing. So for example, we have a requirement for a flight that requires an augmented crew, right? So there are three pilots there. Two of the pilots may come from one pairing, and the second captain can come from another pairing. That's where we see there was a crew splitting. The crew splitting has a trade-off between the crew splitting and the cost of your solution. The more crew splitting you have more chances to construct your solution, pairing solution. Then you have likelihood to have you have good chance of having a better solution cost. And more crew splitting you have means less operational friendly the solution is, because the pilots need to do a lot of coordination during their operations, make the plan harder to follow during when you execute the plan. And also more crew splitting means that you have less stable groups. Right? The third aspect of crew augmentation is a downranking. So example of downranking is let's just say a flight requires augmented crew. You can satisfy that requirement by supplying three captains, where one of the captains downrank to perform the first officer's work. That's what we call downranking. So it is counterintuitive. Look, we're talking about minimized cost. Why adding more crew will reduce your cost? So the simple answer is because you're adding one crew to the flights or pairings, it relaxes the rule around your duties. It extends the longer duration, the duties can be formed. Also, by adding more crew, you can make the pairings more compact by reducing the rest requirements between the duties. Right, here are the examples where I show you this will happen. The first example, what we're seeing here, on the bottom corner, you have the stations. We have flights between A and C, out and back. On the top row, you have daily schedule, 2 flights between A and fly out and coming back to A. So here is the second row is one solution to cover these flights. If you assign a basic set of crew, you cannot fly any duty longer than single flight. Also, you have to have 2 layovers, or we call the rest between those two flights. So by constructing a pairing like this and replicate it over for each day, you can see it covers the schedule, right? Alternatively, that's where the crew augmentation can come in. If you add one more captain, that extends the max limit of your duty. So you can fly out and back in a single day by using the 3 people. And if you compare the cost of these two solutions, just compare these two pairings, because if you replicate them throughout, for each day, they cover the same schedule. Just comparing these two pairings, the cost is that before you're using 2 pilots, 3 days each. Now you can use 3 pilots 1 day. So you save 3 crew days, right? Also, before you use 2 hotel nights, 2 for each pilots in the basic crew. Now you do not use anything. You save money by doing this. Extending to this example, let's assume for each day, the first row again is a daily schedule. You have 2 small flights between A and D in addition to the A and C flights. You have A and D flights out and back quickly, short flights. So by the augmented crew cannot fly any additional flights due to the rules. So you have to, the first solution, you have to assign another set of pilots, basic pilots, to cover these short pairing out and back. So this is one choice, right? But if you assign, in addition to augmented crew, assign additional first officer, the duty can be even extended further. So, and if you compare these two solutions, you will see you save 1 more captain day. Here's an example where adding more crew will reduce the rest requirements. Again, I have the operating flights between base A and B and back every day. I have the first solution to cover that is to use augmented crew to cover the first flight and take a rest of 3 days, then coming back. In the airline world, because the station B is far away from base A, there's many time zones different from base A. For pilots to fly back, right, they usually require them to get acquainted with the local time zone of station B, and it usually takes 3 days to do that. So, however, if you add another first officer, to the second duty of this pairing, then you can reduce that rest requirements from 3 days to 2 days. And how do you bring over the additional first officer? You can do this. Deadheading him on the end of the first day, take 1 hotel night, then coming back, right? Then compare these two solutions. It's obvious we use 1 extra deadhead. That's why we at the expense of using 1 deadhead, we saved hotel nights, right? We added 1 extra first officer hotel nights, but we saved 3 hotel nights over here. A net saving of 2 hotel nights. And the crew days is a wash. So by adding more crew, we reduce the rest requirements, we save cost. Notice at the second duty, in the second solution, right, we have a set of crew which come from 2 different pairings. That's where crew splitting also plays. So to illustrate the usefulness of do the downranking, here is an example of 2 sets of people from 2 bases. Here we have 2 bases, A and B, and we have first set of people is augmented people, crew. Then they fly out from A to B, then coming back. In the returning flight, there's the requirement for the augmentation is only basic is enough. So 1 captain is deadheading back. So in the second set of crew, they're flying these 2 pairings. They are double crew, 4 people. And in the first duty, they require double. In the second duty coming back, which is from B to C, the second duty is C to D, D to B, you only require an augmented crew. So the first officer is deadheading back. If you're an experienced planner, you will notice, hey, I have a captain which is already in station B on day 2. Why can't he continue on and fly this flight and coming back? That's precisely the other solution. We can simply combine these 2 pairings and ask this captain be downranked to a first officer and perform the role of first officer. We can cover the same flight, same set of flights. Everything is legal. They cover the same work. Right? If you compare the cost of these 2 solutions, you will see that deadheads, we saved 2 of them, right? Before you are using 3, now using 1. Also, the hotel nights, because we combined these two pairings, hotel nights remain the same, so no change. The crew day-wise, actually, we saved 3 first officer days at the expense of 2 captain days, because the pay scale difference is a wash. So for most airlines, the second solution is a better solution. So now I've shown you like some simple examples, which involve 4 stations at most, and just a few flights. So that where all 3 aspects of crew augmentation, they matter. Imagine for a real airline, the number of flights in a day could be hundreds, if not thousands, and the number of stations could be in hundreds. So that's, it's impossible for a planner to manually finding all these opportunities, right, to do the savings. You need a model to solve that. That's in the next, I'm going to show you some of these models, all right, in more detail. So this is a quick view of what the basic pairing problem without augmentation. The goal of the basic problem is to minimize the pairing cost. The pairings has to be legal. Over here, it'll be checked on the legality, and then it need to cover the flights with fixed crew requirements and respecting the manpower limits. However, if you want to add augmentation, you need to add the augmentation constructs, the model. You need to model that explicitly, and you also need to add augmentation rules to allow the extended set of pairings to be considered. So that's exactly what we come in. We have an extended comprehensive crew augmentation model, which includes all the 3 aspects we talked about earlier, and we put it into an OR model, and we can solve it. So mathematically, so the basic crew pairing problem looks like this. So there was a lot of literature talking about this basic problem, where we have pairing selection variables. We want to select the pairings from a set of candidate pairing pool, right? So the pairings, we want to minimize the total pairing cost selected, and subject to the pairings need to cover those flights. And we have a set of global constraints where the manpower, for example, the total pairing, subset of pairings which come out of a base, they need to be able to be flown by the manpower that is available from that base. So this type of problem is a MIP problem. The number of constraints is relatively small. However, the number of variables is huge. To give you a simple example, just for a simple 2,000 flights scenario, the possible candidate pairings easily round into 10 to the power 15 quadrillions. And there's a lot of research in the past decades or 2 decades to solve this problem. And a lot of progress has been made. People now can solve this problem reasonably well in a reasonable amount of time with good optimality. The gap is close to 1% of optimality. There's an alternative model in the literature by Vance in '97, which they split the flight coverage constraints into 2 sets. They introduced another variable, which is a duty selection variable. And so the flight coverage constraint was split into using the duties to partition the flights to satisfy your crew requirement. And then the second set of constraints is to ensure that the pairings you pick on the left-hand side only use the duties you picked in the first set. Constraint-wise, still simple, but the number of constraints increased from a few thousands to millions because the number of potential duties increased a lot. So we talk about their model here because our model resembles a little bit like this model, but we consider augmentation. They don't consider augmentation. They only solve for one rank also. The approach they proposed in their paper is also not practical. So it has a limited application. So there's very few paper in the literature that talks about crew augmentation, how to solve this problem. There's only one we found in the literature. That is by Yan and Chan in 2002, where they use exactly the same model as a base crew pairing model. The difference is that here the pairing selection variable themselves encoded the team that is assigned to the pairing. Otherwise, exactly the same model, the approach also applies. We have flight coverage and the global constraints. From mid-90s, Sabre, we have a model already that takes all the aspects of crew augmentation into consideration. And we like advanced, we have duty selection variable, we also have downranking variables. So we minimize the pairing cost. The flight coverage now is duty selection, duty to partition the flights, and the pairings, the basic pairing to partition the flights. It's very similar to advanced, but it's more than that. And the second set of constraint is duty coverage, but this is for per rank. We can solve all the ranks at the same time. So on the right-hand side, it is the duties selected either by the duty variable, selection variable, or the basic pairing selection variable. And any duty selected for that rank, there is a certain amount of people required. That constitutes of the right-hand side. The left-hand side is the people supplied for that rank supplied by the pairings you select, plus the people downrank from upper rank to this rank. All those variables add up, minus the people downrank from this rank to some lower rank. So the constraint is simple, but the number of constraints is, again, millions. Again, we have global constraints. We have this innovative model, and we have had this model since the mid-90s. And since then, the model evolves, but we added a lot. This is our base model, and we added a lot of options to tailor to different airlines' needs. Solution methodology-wise, we've made a lot of change to enable us to solve ever-increasing problem, larger and larger problems, and solution quality has improved as well, and we increased the speed. And during mid-90s, we have the model, and initially we solved it as a MIP model. Just send it to the MIP solver, and then we went through a phase where we solved the problem by generating all the columns, all the legal pairings up front, and solve it using column generation technique. And then we improved the column generation technique we used by incorporating the primal dual subproblem simplex method to solve it. By 2005, these are just a few milestones we have. We have much more work than this. So by 2005, we go into a full-blown delayed column generation approach where we don't generate all the pairings up front. We generate them only needed by using a network optimization technique to solving the pricing problem, which determines the next set of columns to go into the master problem. After that, we've added the dual stabilization technique. We also, to improve the performance speed, also use the branch and price to enhance the solution quality. By now, we're working on a single unified model that can solve both long-haul problem, the crew augmentation problem for cockpit, and the short-haul problem, both for cockpit and both for cabin crew, with all kinds of options available. So this is how our solution looks like today. So I want you to focus on the bottom diagram, which depicts the solution process, your typical solution process. Out here, we have 4 solution modules. They map to the different solution stage of the solution process. So x-axis is the solution phase over time, then y-axis is objective, upper and lower bound. So the first phase is that we solve the LP relaxation of the augmentation model that we have, the last model we have. And then once we got to LP optimal, we go to the second phase, which is branch and price phase, where we iteratively branch on the constraints on variables to narrow down the attractive set of columns to send to MIP. And we do this iteratively. We solve, then the third phase is MIP phase. We solve MIPs iteratively. So we solve multiple MIPs. At each MIP stage problem, we add validating quality, strengthen the formulation, we do heuristic diving, and last phase is a heuristic improvement stage. Once we got a good quality feasible solution, we use heuristics to polish our solution. So as you can see, we've employed many advanced OR techniques from many different areas. Nonlinear optimization technique for convergence, network optimization to get to the subproblem, to solve the subproblem quickly, integer program technique to strengthen the formulation to improve solution quality, meta-heuristic to improve on the existing solution. And all these techniques has been put into a state-of-the-art software system. And this is our pairing system architecture diagram. I just want you to focus attention that center of that system is our optimizers. We have advanced GUI to help user prepare the data, and they can view the data and change it if needed. They can initiate the optimization process. They can have reports to see their solution. So we have a system, and that system is used day in and day out by our customers. And we can demonstrate real-life savings. Here, next few slides we'll walk through in this scheme. We'll pick a set of approaches, traditional, or we call it conventional approaches, compare against our solution on a data set that we pick from our set of our customers, and do the cost comparison and demonstrate our savings. The approach we benchmark against are as follows. The first approach is a naive approach, where it first ignores augmentation requirements. And then, after you solve a basic crew pairing problem, you augment the solution as you see needed for the pairing in the solution in the first step. The second approach we benchmark against is a manual augmentation approach, where the user manually fixes the augmentation requirements for all the flight just by looking at by looking at the flight. They set the augmentation requirements a priori and then solve a basic crew pairing problem. The third approach is slightly more sophisticated. It's to adjust the duty cost, to try to predict how that extra pilots will come in, to account for that extra pilots on that duty. The fourth approach we benchmark against is Yan and Chang's approach, which is an optimization approach, but is quite restrictive in the sense that it enforces that your pilots need to stay on together throughout the pairing, which we don't. So the data set we picked are three customers of ours. The first one is our historic development partner. They have been in production with our system for 20 years, since mid-95. That's the first time we come up with a model. And the other two are a mixture of short-haul flights and the medium-haul and long-haul flights. So these are how long they have been with us. The C is a relatively new client, and this is a fleet they use for these clients. And the data set we use, they're real production data. The first two clients, we use weekly data. The average number of flights per week is 156 for Airline A and 1,500 for Airline B. And for the Airline C, we use the monthly scenario where the average flight per week is around 165. It's not a huge scenario, nonetheless. But here are some interesting facts about your pairing limitations. The maximum number of max length of your pairing is as follows, and the max number of duties in the pairing are as follows. These numbers, if you are in the airline industry, these are very relaxed numbers. This give to a potential a large amount of pairings to consider. So we run the four conventional approaches on these data sets, same identical data, same rule, same costing. We run our approach, and these are the comparison results. This is projected annual savings of our approach over these four conventional approaches. And the green boxes are the approach used for the airlines before they implement our approach. So I want you to focus on them. So for Airline A, the savings is $12 million per annual. And for Airline B and C, it's $1.7 million per annual and $500,000 per year. Percentage-wise, they range somewhere from 5.5% to 11%. For crew pairing optimization, these are huge numbers. In addition to the overall cost savings, right, there are some other benefits. Actually, we observed that this cost savings is across all the cost components. It's not just the overall cost. The crew utilization is increased. We have the number of crew days required for the pilots is less. So they have more room to be assigned days off or training, right? Also, the airline see a reduction in the hotel spending and the travel cost, deadheading cost from the pilots. There are some other, in addition to that, there are some additional benefits reported by the airlines after they implemented our solution. And some of these, like improved reliability during execution of the plan, because we tackle the crew teaming concept head on. And also we improved safety. The solution from our optimizer tend to give more augmentation. So we have more pilots on the plane and obviously safer. And there are some other aspects, like crew is happier because pairing, we have many levels control the quality of the pairing. So the pilots are happier as well. So in summary, I think I convinced you that Sabre has an optimizer which uses innovative OR modeling, which uses advanced OR techniques from multiple different disciplines, and we put them into a solid software system, and that system has been in production for decades, helping our customers generating millions of savings. For Airline alone, Airline A alone, the annual savings is $20 million. You saw $12 million there in the previous few slides earlier, but that's only portions of that fleet data. It's 60% of that fleet data. The annual savings for that fleet alone for that airline is $20 million. And we can solve large problems, like for large airline problems using augmentation model. And we're poised for the future work. There are interesting trends that present challenges, like from the airline industry. The AIDA forecasted in the next few years, the travel demand will increase 6 to 7% every year. Also, there's new regulatory change from the FAA, which allows domestic augmentation, that is not allowed before. Just at the beginning of the year, they start to allow that, and people try to understand the implication of that. And we have a tool to help you already. And also, from a manufacturing standpoint, more fuel efficient and cheaper airplanes are manufactured by Boeing and by Airbus. What does this mean? It means more low-cost and regional carriers can offer long routes flights, and also more airlines can start using the same aircraft to fly a mixture of long-haul and medium-haul, short-haul flights. All these means larger pairing generation problems. And we're right there. We have a solution today that can meet those challenges. With that, I conclude the talk.